Hello, welcome to Vectoria. This is going to be a super quick rundown of how our most important vector quantities relate to each other. So there's a lot more detail that we're going to have to learn about or review again, but this will be just kind of a quick and easy tutorial about how each of these different quantities and their graphs kind of relate to one another and how we can use them to solve problems. So in this kind of imaginary map that I've created, we've got positionville, so to describe where a position is or how far it's gone, velocity for how fast it's moving, acceleration station for its acceleration, and then we can cross the inertia river. Remember, inertia and mass are kind of the same thing, resistance to a change in motion. And so when we cross that, we get a 2 momentapolis if we cross from velocity, or if we cross from acceleration station, we get to force Delphia. So in this little kind of map that I've drawn, there's two different types of motion that I've represented on my graphs. So all the red graphs are representing this positive velocity, positive acceleration type motion. You can see it and zoom in on the graph on your own, but something moving faster and faster and faster to the right all the time. So maybe that's a box, and maybe the box is getting pulled by a string, and there's maybe a little bit of friction, but not enough to slow it down. And so it keeps getting faster and faster and faster all the time. Okay, we've got another box over here, or another object, and this one is moving at a nice constant rate. So maybe this one is being pulled too, but maybe the force of friction equals that tension it's being pulled with, and so it moves at a nice constant rate in the negative direction. Okay, and so it just keeps plugging away in the negative direction. So each of those graphs, anywhere in this map, represent either the blue motion, a constant negative velocity, or the red motion, an increasing positive velocity. All right, so there's some rules that we need to follow to kind of memorize the different connections we need to make. Every time that we move down in our map, so if I go from positionville to velocity, for example, I take the change of the thing above and divide it by time to get to the item below. So for example, position, if I take the change in position or displacement and I divide it by time, okay, I get to velocity. And the rate of change over time is the same as the slope of my position time graph. So that's one of the really important things, is that the slope of a position time graph is a velocity. So something that has an increasing positive velocity has an increasing positive slope. Something that has a constant negative velocity, like this blue motion right here, has a constant negative slope on a position time graph. Okay. Another one of the rules is that if I move up in the map right here, I take the area under the graph from the thing below it. So from velocity, if I take the area under my velocity time graph, I get a displacement, a change in position for how far that thing actually went. Okay, and so this kind of pattern is the same throughout this whole map. So for example, for velocity or velocity, the slope of the line or the rate of change of velocity divided by time equals my acceleration. Okay, so the slope of a velocity time graph is the acceleration. Okay, and for the acceleration, okay, the area under the acceleration graph, that is my change in velocity. So the area under my velocity time graph was my change in position. The area under my acceleration time graph is my change in velocity. Okay. Remember that these areas can be negative. So for example, this blue motion up here represents something moving in the negative direction with a negative displacement. If I took the area under that negative velocity graph, that would be representing this motion. I would get a negative change in position. Okay, and the same thing can be true for acceleration. I can have a negative change of velocity if I have a negative acceleration. All right, if I cross from Velocity into Momentopolis, so if I go across the bridge here, across my inertia river, I get momentum. So momentum, symbol P, is a mass times velocity. If I cross the inertia river from acceleration station, I cross right here, okay, I get to Forceadelphia, and that is a mass times acceleration. And specifically, a net force is a mass times acceleration. Okay, the same rules over here apply if we're dealing with these vectors that are including mass or inertia. The same thing applies. So the rate of change of momentum divided by time, or the slope of my momentum time graph, is force. So that equals force. Okay. If I take the area under my force time graph, that is a change in momentum. That change in momentum has a special name. It's called an impulse. So if you see a force times a time, or the area under a force time graph, that's called impulse. And so we should remember that change in momentum is impulse. We usually use a capital J to represent that. Okay. These forces for the red object, again, must have been unbalanced. So I have this big force to the right, smaller force to the left. So I had a net force to the right. That will always be the same direction as the acceleration. I can't have a positive net force and a negative acceleration. They'll always be linked to each other. Okay, for the blue motion up here, if it's moving to the left at a constant speed, that means I had zero acceleration. I had zero change in my velocity. I had zero change in my slope for my position time graph. So I have to have zero net force. So if I have zero acceleration, I have zero net force. That means all the forces are balanced, not that there's no forces at all. Okay, so that's a super quick rundown. Remember, if you get any vectors at all that are off at an angle, all you need to do is figure out their components and just solve them independently. So, for example, maybe I have a momentum at a certain angle. I just would take my momentum in the x direction, and I would know that that would be my original momentum times the cosine of this angle, assuming this is to the horizontal. If it's not, this would be switched around, but usually I just like to work with my horizontal angles. And I'd figure out my momentum in my y direction, and that would just be my original momentum times the sine of that angle. So don't forget about that. That was a really quick rundown of our vectors that we need to know.